So, part 2, and yeah, well, more or less the same literature. A very good book if you want to look into morphological image analysis is this one. He has describes the methods very well, and also has nice pseudocode if you want to implement it yourself. So it's not in a specific language, but it's easy to follow if you want to understand what is going on in the different algorithms. So now the question is how we can measure sizes of complicated objects. Until now we measured area, we measured perimeters and things like that, but they don't really tell much about the object. And we can also measure sizes for how far things are away from the surface, etc. And we may want to even measure how objects change when they grow. And the other thing is we may also want to quantify how patterns look like inside. And that is inside the object. And sometimes, well, apparently there are some stories that a radiologist says something looks evil. What does that really mean? Probably there is some intensity or roughness in the pattern that makes him telling that it's evil. Here we again have a bunch of new modules. In particular, this one, the distance transform, and EDT stands for Euclidean distance. For the pattern analysis, we use this Grayco matrix, and otherwise there is nothing new, I would say. So let's first look into distances. So the first thing, one thing you can compute is a distance map, and the question is what it is. So this is the logical saying that it's a map of distances, but in principle what it does is computing the distance from the edge of an object either into the object or out from the object. So it's always the distance from the closest point where we have a change. And different metrics can be used, the Euclideans, and there are some approximations of it. City block, which is the 4 connected, and checkerboard, which is the 8 connected. And we can even see the difference between them later. So the first thing we need is some kind of test image. So this should be a circle, as much as we can call it circle, with the foreground and the background. And this will be our test image for this analysis, or for the following steps. And if we want to compute the Euclidean distance transform of this, you can see now that in the background we have zeros, and the first pixel in gets the distance 1. The one here at the corner gets 1.4, and then it gets increasing towards the middle of the object. And this is a very simple object, so everything is very symmetric. And if we look at different algorithms, how to compute it, then you can see that it takes different time. So the exact transform takes about 10 microseconds for this example. If we do it with some brute force algorithm, then it would take almost the double, or even more than the double. And here is another one, which is, say, a smart approximation of the Euclidean distance, and it doesn't do exactly the same. You can see here that we have ones everywhere, so it's in principle. This is checkerboard. Interesting that it was written chamfer, but anyway, so it's an approximation, and then you can see that every pixel that somehow has a connection is 1, and then we have the 2s and the 3s. So you have less variations compared to this and that one. And yeah, that was another thing. You could see here also that this one was a little bit less than 9 microseconds, so it's a little bit faster than the exact transform. Now the question is, why does the speed matter? So for small images, we are talking about microseconds. It doesn't really make much sense, make much difference. But if we're now talking about huge data, so we are talking here about quite many pixels. So it's 8 gigavoxels. No, even, yeah, say 10 gigavoxels. And these actually have even more. If you say it's in bytes, it will of course be more. And if we want to compute distance transform of one such image, it may be okay, but if we have a series of, you may remember from this bone experiment I talked about in the beginning, there were, I think, 1,000 volumes of that kind, then speed actually does matter. And every microsecond you can squeeze off in the small case, that can be really paying off. So here's an example where we have a disk. Now the image is 500 by 500, and we compute the transform. For this case, it took about 14 milliseconds to compute. Still small number, but if we extrapolate it into what this big image was, then we would say it's 20%, so it's 0.2 hours. And if we use the brute force algorithm, that would be almost 6 hours to compute. So here you really see the difference. And if you use the chamfer, which is an approximation, then you can get in 0.0 hours. So it's already here a factor 5 between that one and that one. But the cost for doing that one to that one, you already probably see that you have this kind of bulged diamond shape, and that is the cost of the approximation. Sometimes it's fine. You may not need the exact distance value, but you need the speed. And cases when this is useful, I'm going to talk about next week when I'm talking about an alternative to the component labeling we talked about for the break. Then you need actually a distance transform to as input data. Then what we do, in principle, we have an image with foreground and background, and the distance is computed. There are different ways. You can do it as a Euclidean distance, you can do it as an absolute distance, absolute difference between the two places, and then that relative to the background. And well, here is a small example. What we do is, in principle, we have a loop over x and y, and if we are in the foreground, then we start doing some more calculations. And these more calculations are looking in the neighborhood, so plus minus 1 pixel in x and y. And then we compute the distance metric, and that is the value that we then put into the pixel. Just a comment, I will not expect you to recite this during the exam. So all the code examples, they are just to explain how it works, but I'm not expecting any of this code to be recited during the exam, so don't be afraid of that. So let's do a test image of the distance transform that we just implemented here. And you can see this should run. It does, yes. So now you can see how the distance is propagating in from the edge towards the middle. And also for distance transform, there are many algorithms to compute it. And what everybody are aiming for is having the fastest way of computing it. And there are even, I think nowadays there are even some parallel algorithms. I haven't actually checked that implementation side, but it is a time-consuming task to compute this, because you always have to look around in every neighborhood and computing a lot of distances. And it is a considerable part of some analysis to compute. So therefore, people have put some effort in speeding it up. A different distance metric would be to just take the absolute difference between instead of the Euclidean distance. And same kind of code. We are going through the image over the neighborhood, and then we have the absolute difference between the two. And what that looks like, you can see here when we iterate. No, there it is. And now you can see that it comes more like in concentric rings instead. So this is another way, not as exact, but mostly faster. Another thing to think about when you compute the distance map is normally we are kind of anticipating that the voxels or pixels, they are isotropic. Then it's fine. Then you can just use the algorithm as it is. But in some cases, for example, in medical imaging, you can have anisotropic voxels where the CT scanner has produced. And they have some pixel size on the slices, but the thickness of the block may be different. And then it can be misleading if you just apply the traditional available distance maps, and possibly you need to implement something yourself, or I wouldn't be surprised if there somewhere is some distance transform where you can add how long the pixels are in the different directions. So this is something to pay attention to if you're working with that kind of data. And what it shows, we can actually create two different types of distance map, one going into the object and one going away from the object. And if you look at this bi-level image, some kind of an ellipse, then you can see what it looks like when you are going from into the foreground and see the distance, or the other way around, the distance from the object, and then you can see it in that way. Depending on what you want to do, you can do either one of them. And it's not so difficult to actually to produce it, because you can just set or reverse the images. So if you have a black and white image, it's one minus image, and then you can get the other one. And then we have a little demo that shows the effect of two images. For that we need some code, which I'm definitely not going to talk about, but we need some code to do this animation that we need for the next slide. And here we have the distance map. It should be running. No, there it is. So we start out with two ellipses and we let them grow. And what you see now is that if we compute the distance map of this one, you get the values. There is some average value, the average distance, and you can see that it's growing a little bit when the items are growing. That reflects actually the growing process. If we instead would do component labeling the two objects, then when they grow together, it all of a sudden turns into a single object. And that is what you see here, that you have area of component 1 and component 2. And then when they grow together, there is a jump, and all of a sudden you have a huge area. And that can be very misleading if you have touching objects when you do the analysis. So maybe you need to change the way how you do the component labeling, which is next week. No, it's not next week's lecture. It's in 2 weeks. We have Easter holidays next week, so in 2 weeks. But anyway, you can see here the effect of things that growing together, and then you can get a jump not only in the count of items, but also in the perceived area of these items. Now to look at, now we just looked at some toy examples. Now let's look at some real images. And the bone slice that I have shown before. Here we have a mask which looks like this. And if we look at the foreground distance map, you can see that we have some colorful small dots in here. The large one, of course, turns into even the whole rainbow, but the other ones, they don't get much up. There's just a little bit of blue with a brighter center. If we, on the other hand, look at the background, it looks more psychedelic. And then we can really see the distance between the different items. And it shows you how we can actually use this in a way to separate the objects and how far away they are from each other. Another example would be to look at the cortex. Here we are not even thinking about what the structure is, just that we have this curved mask. And you can see that it gives us a ridge in the center line, and then the distance is decreasing toward the edges. And if we look at the details, you can also see how the distances look like. In this case, I'm just looking at the integer values, but it's actually an Euclidean distance. And it's also every fifth pixel, otherwise I couldn't show the numbers. Oops, wasn't meant to. And if we look at the histogram, we see a large peak of the zeros, which is the background, so that's not so exciting, but can also see that how the distances are distributed. And as we have something that is a little bit asymmetric, we can see that it tapers off quite a lot towards the longer distances. An example how to use the distance transform in some kind of measurement is actually a longer evaluation. And if you are interested in how to do this, there is a whole notebook which is dedicated to it. So if you just click on the link, then you would get there. But I'm going to just outline the analysis. We had some soil sample, and they wanted to look at how wet or how dry the soil is on the depth as a function of distance from the surface. So instead of just taking a straight line, which you see that it is not, you can see how wavy the surface is, we computed after some pre-processing to mask out this circular area. We computed this distance map. In the beginning it's quite faint, so you don't see it. But you can see that the distance is increasing here. And what I then, did was to, for every distance with the precision that I wanted, I think I took the integer distances. For every distance, I computed the average intensity in this image. And what we can see, first it's some kind of a transmission on the surface, and then you can see that in the beginning it is less transmission, and then when we get deeper, at some point it gets quite a straight line down. So we can see how this wetting front is behaving. So this is actually the intensity intensity average in that direction. The blue background is 1 standard deviation off from the line. And it shows also that it's quite homogeneous in the distribution in that sense. An alternative to the distance map, which just tells us where the distance is, we can use the thickness map, which more tells how large is the largest sphere you can inscribe in some area. So if you have this big blob here, the thickness map tells how large is a sphere I can inscribe in at this point. That is something that is used a lot in porous media research, and to describe the porosity in the media. And you can see here is an example. This is a ball packing, so I had stacked 8 balls together in 3D constellation. And if you look at the distance map, you can see that it's always the distance, so we get a ridge between these objects. And if you look at the thickness map instead, you can see that it's actually having much larger areas because you have large balls that can be filled into these areas and smaller balls here. So an example of that was done by my colleague Peter Lehmann quite a while ago, actually. And he shows how the different distributions look like, and that in the end he could also derive into how the water flow was going through this sand packing. And implementing it is actually based on the distance map, and then you sort the distance map and fill in spheres in the image depending on the distance. And oops, wrong way. So, and now we look at the thickness map of foreground and background of an image, and that one should have been executed. There we go. No, I need to go back. Yeah, that takes a little while. Yeah. So this is maybe not the most efficient implementation, but again, so now we can see it. And this, yeah, so now you can see here, there are some pores here in some material, and you can see first this is just plain blue, but in this case it's not a fully perfect sphere, and the effect is then that the closer you come to the edge, you will have some different radius that comes in. Same goes for this one, where you look at the distance between these holes. This is almost a sphere, and the sphere can be squeezed in a bit here, but then at some point the radius have to decrease, and then you see a difference in the colors here. Looking at the thickness distribution and compare it to the distance transform is that if you have the distance map, you have a lot of pixels which have distance 1, already quite less for distance 2, and so on. But if we look at the thickness map, we can see that we actually are centering around some specific sizes. And that is actually the information that is more relevant if we want to quantify what the porous medium looked like. Same here. You have a lot of distances, they're peaking up here. But again, in this case, you can see that you have 3 main distributions that you are looking at in the thickness map. Of course, we can also do distance maps in 3D. I didn't show it until now, but in the 3D, it requires a little bit more thought to implement. But we have here, this was a bubble example, I think. And here you can see how the slices look like. Was some compressed sand too? No, it was bubbles. And you can see that in the from the top view, you have looking like just round pieces, and from the side view, you have ellipsoids that are packing up. And that we can look into, actually I should have hidden that code, as some kind of 3D mesh. And just to have an idea what it looks like. And we can also look at it as a surface rendering. And if you want to do this, there are some nice functions that I have hidden in the code. You can also look at the ISO level from which no, I thought I should. No, yes, I need to press the random to let it happen. So. And now to look, just compute the distance transform, we get this typical pattern that we have always some peaky points in the pore space and everywhere, and also from the side view. And now to compute the thickness map of the same, we can look at, or actually this must be out of foam, also some bubble thing. Here you can see very nicely how it's cut, that we have 3 millimeter radius of this bubble and much less down here on the smaller ones. So when it goes towards purple, we are down here. And this gives us an overview of how large the bubbles are in this material. And this algorithm found in the data I used 98 bubbles, and then we can look at it. And this way of visualizing it is, before I showed you the 3-dimensional, where you can show some isosurface, this one has a different information. It's the maximum projection through the volume in different directions. And it tells us that somewhere in the data we have some very thick bubbles, but mostly they are about the same. And again, same view as different views. You can see also that there are some hotspots which are larger, but the rest is about the same. And maybe towards the edge, it's also tapering off a bit. So this is an alternative way. Yet another way to look at it is to just take all the slices again through the bubbles. And here you can also see when you pass through the stack. So this is the top, and then it goes down, deeper down, all the way to the end. And same thing for the bubble from the side view. What you choose depends on what you want to do. And I would, for example, say this is probably something you more use for your own purpose, just for your own communication or talking to your supervisor. It's a lot of information. This one you may have to explain a bit, but it's already closer to maybe a publication. Depends on, again, what you want to show. But exactly, it requires to explain what you actually see. And of course, you can also go for the 3D view, and then you can play with rotations and cut planes and see what it looks like. You can play with the opacity, depending on how dense the packing is. And this is just a simple way of showing it in Python, but there are tools that are more dedicated for doing this. So this particular show is more for your own purpose when you're working with the data. If you want to do the final presentation of your data, you probably need to use some different tool. And the next thing we want to do is to look at different interfaces and surfaces around the object. And for that, we want to compute, for example, the surface area or perimeter of an object. And that can be done using erosion and dilation, for example. And another way of describing the surface is to use a mesh. like you see here. I also showed it on the bubbles before. And these meshes, they are not only useful for visualization, but you can also use them if you want to plug it into some finite element simulation to simulate whatever physical process you want to look at. Can be a flow field, magnetic fields, whatever. Oh, of course, also you can do some loading on it and check what happens when you put some forces on the system. The meshing is a task of itself, and it's done using something called Martian cubes algorithm. And the reason for using the mesh or Martian cubes is that, as you can see here, I think I already showed this example, is that when you have very small objects, you cannot describe them very well with just the voxels. What the mesh is doing is trying to interpolate what the shape would really look like, and the Martian cubes algorithm is looking in either on 2D a 2x2 area, and in 3D is a 2x2x2 area. And depending on the constellation of the pixels in this area, you can get different polygons that you can bring in, or triangles actually, that you bring in for the meshing. And with that you can make a much preciser description of these objects. One more thing we can measure is the curvature of the object, and the curvature is mathematically defined as 1 over the radius. So a low curvature means then that we have a very large radius, and reverse, of course. And that can be used to describe the surface normal, and the surface normal again can be used for simulations, and also a very important application of it is in computer vision or computer graphics, when you want to describe the reflections from objects. So the people who develop games, they look at that very much to make more photorealistic visualizations of their surroundings. And to measure the curvature in 3D, then all of a sudden, if you have a curved shape, then you can describe the curvature in 2 directions. So typically what we do is to look at the maximum curvature in some angle and the minimum curvature in the same angle. So it's orthogonally described. Then we are looking also for the 3D. We can look at the mean curvature or the Gaussian curvature. Again, which kind of curvature you look at, again, depends on on your analysis when you want to do it. So that is something you have to explore, or maybe physically motivate which kind of curvature you are looking at. There's a 3D example. It's not so easy maybe to see the differences between them, but it shows at least some example how it's displayed. Then we have some characteristic shape, and that we can describe with the help of the curvatures. And if you have different, you can describe how objects change depending on these curvatures. So if you have here, you have some annealing of solid, then you can go from spherical phases to more another kind of shape depending here. So you can see very much from these curvatures. You can of course examine how the interface or different interfaces look like. If you have a lot of folding, if you have a lot of saddles in your data, and can also give some visual indication if you plot it of structural changes. And important is also that it is scale free. when you assess the structures, because some other metrics, if you just look at the surface area, it depends on how large it is. But if you have an average, the mean curvature, it's a scalar that is not depending on the scale. And other things we can look at, but would be to do some directional analysis. So we can also look at tubeness or surfaceness of different shapes. Can come into even fractal analysis to describe how a material is looking. And this would be quite detailed, so I leave it with that. And of course, it's a popular topic, so there is a lot of literature if you are interested in looking into it. And with that, I leave the curvatures and the distances and shape descriptions and go into a different topic, which is the texture analysis. And textures is something, in principle, patterns. And in the world, we have a lot of patterns. So here are some nature patterns. So you have leaves, some seeds, rocks, soil, a wall, an ocean. This is fireworks, I think, and so on. So there are many different patterns out there. And now if we in the image analysis want to look at or describe these patterns, then you can find a bunch of metrics which is described by these hierarchic texture features. And if you want to look into that topic, there is even a DOI for it. Today, so that was a focus in many years. Today, a lot of this has been reduced into doing some kind of machine learning task, identifying based on these patterns. But it's still good to know a little bit about some metrics that you could use to describe the patterns. Sometimes you actually want to put some quantitative number on the pattern description. For the example, I'm going to produce some test images. So we have here stripy patterns, dot patterns, bit noisy, unsharp patterns, again the dots, or diagonal stripes. And these we are going to check with something called the co-occurrence matrix, which is quite a complex beast. It goes from 2D into 4D, and what it measures is difference in gray level at distance from the current pixel. And that is what all these variables are talking about. And it's not so easy to do this 4D representation, so we try doing our best. For that we need to do some code, but in the end we end up with some values that can be measured. Typically it's not only distance but also rotation, and that we are looking at. So in this example we are looking at 4 different gray levels, 15 distances and 15 directions. And that gives, gives us some co-occurrence matrix plots. So we have the test patterns here, and this is actually a mosaic of different co-occurrence plots. And you can see that the flat ones, they are only representing a single row in this matrix. And the reason is that we only have actually 2 gray levels to play with. So we only have black and gray. And that's why we don't get anything else down here. And same goes for that one and that one. And something that you possibly can see as in this one is that there is a flipping depending on the orientation between that one and that one. They should be more or less the same. Like that one is also something similar to that one. The dot pattern looks a little bit different, And when you get into more gray levels, you can see that it fills out here. And that is because we have more gray levels to play with in this analysis. Something slightly confusing to me actually is that the average co-occurrence for all of them turns out into the same pattern, which didn't make sense to me when I ran it, but that I actually have to do some homework on and check out why it actually happens like this, because that doesn't make sense. So maybe I have a bug in the code. Then we can also work with correlation in different groups and look at how different regions are correlating with each other, and that gives us another, let's see here. So here is the correlation in distance, and here is with rotation. And you can see that if you look at this one, that it goes from not correlated at all with the distance to very correlated, and then it goes down. So it goes up and down like this. Why that one looks like this? That's strange. That one has a little bit more like that one. This is now confusing. That one I have to go home and check on. Sorry. But let's look at a practical image. So I got some images from a sea urchin. It's I think it's a microscope. And this is what they look like out in the sea. And if we look at a microscope image, I tried to identify different regions. So this is my layman markup, but I think there is one area out here which is quite much the same, and then there is something that's a bit denser, and then there is more consistent region here, and then there's a brighter area out here. So I tried to mark it up like this. And if I overlay it with these regions, it looks like this. And then I tried to do some texture analysis based on this, and we are looking at different properties that you can measure texture with. And typically we want to identify regions using the textures. So we load the images, maybe we do some create some annotated mask. For this kind of analysis, we need to look at smaller regions because we need to have some statistics and where we can measure, so we have to tile it. And then we compute some feature vectors of different kinds and compute a co-location matrix and different properties from it. And then we look at the histograms and in the end possibly do some clustering between these groups. Of course, we can come with other ideas how to identify these feature vectors, but now as I've shown the co-location matrix, this is what we are going to look at. So first step is now we create the tiles. So we just make small boxes, and you can see here that all these look more or less the same, and then there is some change in the structure in the different regions. And the size I used is 1 out of these numbers. So if I factor the image, this is what I can come down to. And so in this case, I choose to work with relatively large areas and to have some better description of the behavior of the region. Then we look at different co-location properties. So we can look at contrast, dissimilarity, homogeneity, correlation, ASM. These we can compute with the help and store in a dictionary for each of these tiles. And that's a lot of code for doing it. And afterwards, we have now our images, and this is just the regions that we have computed. Then there is some contrast, the similarity, homogeneity, correlation, and ASM. And this brings us to this table, which is not so easy to interpret. Of course, we have then averages, standard deviation, min-max, and different quantiles. A different way of showing it is to use this pair plot, and then we can start hopefully seeing some regions that make sense. And the ones I'm looking at, so we have the intensity mean, we have the standard deviation and contrast, and so on. It looks like the blue one separates itself, or it's very homogeneous, while the other ones are spreading out. And now I'm going to just look at a little bit more detail. Let's see. Yep, there we got it. Just need to restart the slide. So that should be better. No, doesn't want to. No, it doesn't want to. But anyway, so now we can see we have the intensity mean and the standard deviation plotted against each other. The blue one should be quite easy to separate. The green one, possibly. The red, yeah, maybe. But the orange one is a little bit more difficult to get. But this would be maybe something we can use on k-neighbors neighborhood training or something, or k-means, possibly. And, well, I didn't take it all the way. So, that brings me to the end. So we have now been talking about distance map, a little bit about visualization, using meshes, describing surfaces, and finally a little bit around textures. And these were, say, the traditional way how to approach the textures, but today I would guess a lot of the texture analysis falls into the field of machine learning, because it's mostly quite complex to describe these textures. And yeah, that was the end.